Hello everyone and welcome back to the binary search series, and this is practice problem number 2, and we'll be discussing two sum problem today. So this problem in itself might not be very elegant, in the sense you might not directly find this problem, but today we'll be discussing four approaches to solve this problem, and I cannot stress enough how important it is to understand all the four solutions, because these solutions are really extensible in the sense that all of these four approaches can be applied to multiple different problems and multiple different scenarios. So if you're clear with these strategies, if you've understood the concept and intuition behind all the four approaches, there will be plenty more problems which you will be able to solve with either one of these. So yeah, stay tuned and try to understand all the four approaches very thoroughly. With that being said, let's get started. The question is that we will be given an array of integers, and this array will be in sorted order, and then we'll be given a target. Now we need to return a pair of two indices whose sum is equal to this target. And the additional information given in this problem is that the input array is always going to be sorted. There's going to be exactly one solution, so we don't have to worry if there are two solutions which pair out of these should be written. So there's going to be exactly one solution, and we cannot use the same element twice. For instance, if there's an element 3 and the target is 6, we cannot return 3 comma 3 or the same index, a pair of same indices. We need to have two different indices in a pair that we're returning. So that's a brief summary of the question. Now, the very first naive approach that comes to our mind is that, let's take an example first. And let's say that the target we are trying to search is 23. So a very naive approach that comes to our mind is that we start picking element one by one. So let's say if we have picked 3, and in the remaining array, so the remaining array in this case would be 7, 9 and 14. In the remaining array, we try to find out an element which when added to 3 gives target as 23. Now, saying that in the remaining array, I want to find an element which, when added to 3, will give me 23, is same as saying that in the remaining array, I'll try to find 20. So, 23 minus 3. If I'm able to find 20 in the remaining array, then obviously that this difference when added to 20, when added to 3, is going to give me 23. So what we are trying to do is that we are picking elements one by one, and in the remaining array, we're trying to find the complement. And complement in this case is target minus the element, the difference between the target and element. So we pick 3 and we try to find if there's 20 in the remaining array. Now, obviously, 20 is not there in the remaining array. So we discard 3. Now we move to 7. And in the remaining array, we try to find out 23 minus 7, which is 16. Obviously, we'll not be able to find 16 in the remaining array. So let's, in this step, we'll discard 7. In the next step, we'll pick up 9, and the remaining array here is just 14. And 23 minus 9 is 14, and we have found 14. So we have arrived at an answer, and it's given in the question that there is going to be exactly one answer. So we have found our answer. So we can return the index of 9 and 14 as our answer. Now, what is the time complexity of the solution? Let's discuss the time complexity of the solution. For first element, we are going to traverse the next n minus 1 elements. So in the worst case, let's assume that for my first element, there does not exist a solution in the remaining array. So we're going to traverse n minus 1 elements. So in this case, when we pick 3, we had to traverse 3 elements, which is, and the size of the array was 4. So n here was 4. So we had to traverse 3 elements. So first element, we traverse n minus 1 elements. Now, when we pick 7, or the second element, we are traversing n minus 2 elements, which is n minus 2 is basically representing the remaining array. So we traverse n minus 2, and so on till we have reached the second last element. For the second last element, we are traversing just one element, the remaining last element. So for the second last element, the number of operations is 1. Now we know that the sum of this series is nothing but n minus 1 into n by 2. So we can easily say that the time complexity for this solution is going to be of the order of n square. So we can say that the time complexity of the solution is big O of n square. Now let's try to optimize this strategy further. What we are trying to do is that we are trying to search the complement of our number in the remaining array. But one thing that is given to us, did not use one information that is given to us, that the array is always sorted. So we know that once we have picked an element, the remaining array is always going to be sorted. So if the remaining array is always going to be sorted, why do I need to parse it linearly and do a linear search on it? A very simple solution could be that I do a binary search on the remaining array, and in this binary search, I try to find the complementary element. So if the original array is 3, 7, 9, 14, what I do is that I pick 3, and in the remaining array I try to binary search 20. So obviously the binary search is going to return us -1 because there's no index at which 20 is present. So similarly we'll discard 3 and then we'll take 7, and in the remaining array we'll try to find 23 minus 7, which is 16, and then 16 will also not be found, and then we'll pick up 9, and in the remaining array we'll try to find 14, and obviously 14 will be fine. We'll be able to find 14 with binary search, so we'll return the answer. Now let's try to analyze the time complexity of this approach. So to calculate the exact time complexity of this approach, we need a little bit of mathematics, but we'll try to calculate the time complexity without actually going into the math part, and we'll try to use our intuition. So let's try. When we pick the first element, we are applying binary search on a remaining array of size n minus 1, and applying binary search on n minus 1 size array is going to take time log of n minus 1. Then again for the second element, we're applying binary search in an array of size n minus 2. So similarly, for the second last element, we'll apply binary search in an array of size log 1. Now, with a little bit of mathematics which involves integration and inequality, we can prove that the upper bound for the sum of the series is going to be n log n. So this is not a very tight upper bound, but yeah, it is a asymptotic upper bound for this series, and thus we can say that in the worst case, or the worst case complexity, or the big O complexity is going to be big O of n log n for this particular solution, right? So this is our approach number 2. So our approach number 1 was basically applying linear search on remaining elements. Our approach number 2 was basically applying binary search on the remaining elements. Let's move on to approach number 3. Let's again take our example array, and try on this. We'll understand the third approach on the same example. So till now what we are trying to do is that we are picking an element and we are trying to find the complementary number in the remaining array. So what if we try to do the exact opposite or reverse of what we have done in approach 1 and approach 2? Instead of finding complementary in the remaining numbers, what we do is we try to find the complementary in the numbers we have already seen. So for instance, if I'm standing at 9, I try to see that if I have found a complementary number in the array which I have already traveled or already traversed. So the complementary number for 9 is going to be 14, because 23 minus 9 is 14. But uh, in the array which I have already traversed, there's no 14. So obviously, I will not get an answer. Then I'll move to 14, and the complementary is going to be 9, because 23 minus 14 is 9. Then I tried to check, was I able to find 9 in the array which I have already traversed? And yes, we were able to find 9 in the array which we had already traversed. So we have actually found a pair, and we'll return this as the answer. Now, to do this very efficiently, we need some kind of a container where we can insert and look for elements in a very optimized manner, because as we are traversing the elements, we'll keep inserting the elements into that container, and when we are at a particular element, we need to find the complementary number, or we need to search the complementary number in that container very efficiently. If we are able to do that very efficiently, then we'll be able to solve this complete problem efficiently. Now, the data structure or the container that comes to mind uh, is obviously a hash set, because a hash set on an average gives you the time complexity of insertion as big O of 1, and the time complexity for lookup or searching also as big O of 1 on average. I'm talking about the amortized time complexity. So in some particular cases the time complexity may be more where you need to rebalance the hash set or rebalance your load factor. So all those details we'll discuss in the maps and sets series. But till then, we know that on average, using hash set, you can get the insertion and searching complexity as big O of 1. Now, having said that, it is hash set in Java, I guess, but in C++, it is known as an unordered set. So, what we are trying to do is that let's walk through this example using this approach. So we are at 3. Now we check that is complementary of 3 available in our hash set. And since our hash set is going to be empty, we have added nothing to our hash set right now. Obviously 20 is not going to be available in our hash set. But after doing this, we'll add the current element to our hash set. So our hash set was empty right now. After this, the hash set will become 3. Now we'll move to 7. We'll check if 23 minus 7, 16 is present in our hash set. Obviously, this will be done in O of 1 time. 16 is not present. So obviously we have not got our answer. But what we'll do is we'll add 3. 3 was already there. We'll add 7 to our hash set. What next we'll do, we'll move to 9. And we'll try to check if 23 minus 9, which is 14, and we'll try to see if 14 was present in our hash set. Obviously 14 is not present, but what we'll do is that we'll add 9 to our hash set now. Then we'll move to 14 and we'll check that 23 minus 14, 9 is present in hash set or not, and obviously 9 is present in our hash set. So we have found our answer. We will return this answer from here. So this is the third approach. Let's try to analyze the time complexity. So about the time complexity, we know that searching and insertion is taking O1 time, and apart from that, we are just traversing the array once. So traversing the array once takes big O of n time. So overall time complexity of the solution is going to be big O of n. Now, what is going to be the space complexity for the solution? So basically, the extra space or the helper space that we are using is the hash set, and the maximum size of the hash set can be equal to the size of the array. So the helper space that we are using will be of size n. So our space complexity also turns out to be big O of n. Now, if we compare our previous solution, that is this, and we compare our current solution, we have actually reduced the time complexity. So the time complexity has reduced from n log n to big O of n. But while reducing this time complexity, we actually added an additional space complexity, and the space complexity that we added is big O of n. So now let's try to see, is there an approach where we can actually reduce the time complexity to big O of n without introducing an additional space complexity. Now let's discuss the final approach for solving this question, and it is a two-pointer approach. Now usually the procedure I follow is that we look at the problem first and then we try to observe the hints or indicators, and using those hints and observations we try to come up with an approach. And I usually do not like the questions where we see the approach first or which have a very peculiar approach. We see the approach and then we try to figure out why does this approach work, because it's really counterintuitive. Because in interviews or in your day-to-day work or in your jobs, you might find a lot of problems or use cases which are new and you might have not seen those before. It's a really likely scenario that you might not know that what approach needs to be followed to solve a particular problem. So you should have the skills to be able to observe hints and observe the indicators to come up with a approach to. You should be able to figure out that which algorithm is applicable here and how can I come up with an optimized approach. But for this particular question and for this particular solution, I am actually going the other way, because as I said earlier that this approach, you might not be able to come up with this approach directly if you have not seen this before, but once you understand this solution is highly extensible in the sense that this solution can definitely solve this problem in an optimized manner, but this solution can be extended to a lot of different problems. So let's first try to understand the algorithm, and then we'll try to figure out why this algorithm works and what is the intuition behind this algorithm. So the algorithm is pretty simple. So we initialize two pointers I and j. I is initialized at 0 and j is initialized at the last index. Now what I and j does, these two pointers basically represent the remaining array. So using these two pointers, I'm trying to keep a track of what elements are still under check and what elements have been discarded. So right now, initially, I'll be considering my complete array. So that's why I've initialized to both the pointers at the extreme ends. Now the main part of the algorithm is that we try to find the sum of the elements at both the extreme ends, or we try to find the sum of the elements pointed by the pointers. So we'll first store this sum in a variable called sum1. Now if this sum is equal to the target, so now you have found a valid pair of elements that add up to the target. So you have got an answer for your problem, and then you can return the pair of indices for those elements, and that would be the answer for this problem. Now the other two cases are, if the sum of the elements is less than the target, then what you do, we move the front pointer by 1. So we move the front pointer, that is I, towards right, and we move it by one step, so we do an I plus plus. If the sum is greater than the target, then we move our end pointers towards left, and every time we move it by one step, so we do a j minus minus. Now what we need to keep in mind is that, or the very important thing is that I always moves towards right. So there will be no case where I has moved towards right in a previous situation and then we'll again move I towards left. So I will always move in one direction towards right, and j also similarly will only move in one direction, that is towards left. So there will be no case where j has once moved towards left and then in some other step or some other iteration we'll move it towards right. So both the pointers move in just one direction depending on these two conditions. So this is the whole algorithm, and this step is repeated till my I is less than j, because I and j are two pointers which is keeping track of the remaining array or the array under consideration. If the starting pointer of that array crosses the end pointer, then that implies that is not a valid array, or the remaining array is of size 0. So if the two pointers cross, there's no element left to be considered. So we repeat these steps as long as I is less than j. Now let's try to dry run this algorithm on an example. I've chosen an example in such a way that we'll hit all the possible or different cases in this example, and that will clarify all our doubts related to this algorithm and give us a very good understanding of why this algorithm works. So the example array that I have taken is 3, 7, 8, 9, 17, and the target I am trying to find is 17. So basically I need to find a pair of elements which add up to 70. Now what does the algorithm say? The first step of the algorithm is to initialize two pointers at the extreme. So I is equal to 0 and j is initialized at 0, 1. So I'll just put the indices above, and j is initialized at 4. So now what I do is that I find the sum of the elements pointed by I and j, and the sum of the elements pointed by I and j is 20, which is actually greater than the target. And what does our algorithm say? My algorithm says that if my sum of the elements is greater than the target, I move j towards left. Now if I move j towards left, my j will become 3 and it will start pointing to this element. Now why does this step make sense? This step makes sense because we know that our sum of the elements is greater than the target sum that we want. So the only option is to reduce the magnitude of this sum. And to reduce the magnitude of this sum, the only two options are either I move j towards left or I move I towards left. Because I have a sorted array, and in sorted array if I move towards left, I will get a smaller element. Now since my I is already initialized at 0, there is no option to move I towards left. So the only available option is to move j towards left, and that's exactly what we have done, or that's exactly what our algorithm tells us to do. So for this case, we have understood the logic of moving j towards left. So you'll probably wondering that what if there was an option to move I towards left also? I was not at 0, somehow I was at some other index and we could have moved I. So that case will also come in this example, so just hold tight and we'll discuss that why during that case also it would make sense to move j towards left and not I towards left. So yeah, just hang on. Now we again find the sum of the two elements pointed by the two pointers. The sum of the elements is 12. Now 12 is actually smaller than 17. And what does our algorithm says? So algorithm says that when the sum of the elements is less than the target, we move I towards right. So by that logic, I will move I towards right and I will now become 1 instead of 0. So now this is going to be the current state of the pointers after this loop runs again. Now let's try to understand why does this step make sense. Now this step makes sense because the sum was actually smaller than the target sum. So the only option we have is to increase the magnitude of this sum. And to increase the magnitude of this sum, the two possible options are we either move our j pointer towards right or we move the I pointer towards right. Now moving j pointer towards right would make no sense because we know that we have already tested that case. When our j was at 4, the sum was actually greater than the target, and that's the only reason j was moved towards left. Since we have already tested that case, so keeping I as fixed and then moving j towards right would not make any sense because we would be rechecking a case which we know would not give an answer. So the only possible option is to move I towards right again and keeping j as fixed. So again our algorithm makes sense even in this situation. Now let's try to calculate the sum of the elements again. So the sum of the elements is 16 and 16 is again less than 17, and algorithm says when our sum is less than target we move I towards right. So I in this case will become 2. Now let's try to understand why this step makes sense, and this condition and this particular scenario is the most interesting one. So again we said that the only two possible cases to increase the magnitude of our sum is to move j towards right or I towards right. In our previous situation we proved that moving j towards right would not make any sense because we had already tested that scenario and we know that scenario gave no answer, so obviously it would make no sense to move j towards right. But now our I was at 1 and j, so I was basically here and j was at 3. So we now you can say that we could have moved j at 4 because I equal to 1 and j equal to 4 is not a case that we had tested, right? So earlier I equal to 0, j equal to 4 was a case that we had tested. So we said that moving j towards right made no sense, so we shifted I towards right. But I equal to 1 and j equal to 4 is a case we had not tested. So why did not we try to increase the right extreme element and see if it is equal to the target sum? So see, this logic is also pretty interesting. So we have seen till now that I only moved towards right. There was no situation when I moved towards left till now. So I has been moving towards right. So let's try to think when j was at 4, I would have been actually at the current index or an index smaller than the current index. So if my I currently is at 1, so when j would have been at 4 in a previous situation, I would have been at 1 or it would have been at 0. There's no other possibility because I did not move towards left. We know that I has always moved towards right. So when my second pointer was at j equal to 4, I was at 1 or 0. And during that situation we move j towards left. So definitely we know that j equal to 4 must have given a sum which was greater than our target with an element that was at 1 or 0. Because see, since the only two possibilities for I were 1 comma 0, and if j was at 4 and somehow j came at 3, then definitely when j was at 4 it would have given a sum greater than the target. Now if in a previous situation j gave a sum greater than the target and I has only moved towards right, so the element at I has only increased. Now if we put j again at 4, we definitely know that it is going to give us sum greater than the target with this new element. So if j gave a sum which was greater than the target with the smaller element, then definitely j equal to 4 is going to give you a sum which is greater than the target with this new element, because this new element is definitely greater than that previous element since I has only moved towards right. So by that logic we can say that moving j towards right would never make sense, because if we move j towards right we are definitely going to get a sum which is going to be greater than the target, because we have already tried out j equal to 4 with a smaller element and since j equal to 4 always was giving a sum greater than the target, that's the only reason we moved j towards left. And that, and the same logic applies on I also. We can conversely prove that using this logic I will only move towards right, because we have already tested the elements on the left and we discarded the elements because they were giving a sum smaller. So if my j is reducing, so these smaller elements will definitely give a sum smaller than the target now also. So by that logic I should always move in one direction and j should always move in one direction. So now moving j towards right does not make sense. So the only possible option is to move I towards right, and that's what we have done. So now we have actually proved that in all the possible three scenarios, it always makes sense to move I and j only in one direction. If the sum is less, we move I towards right, and if the sum is greater, we move j towards left. So our algorithm, when discards an element, we do not need to consider that element again. So now since we have understood the logic and intuition of our algorithm, let's continue with our example. Now I is equal to 2 and j equal to 3. Let's try to find the sum of these two elements. And the sum of these two elements is 17, which is equal to our target. So now we can easily return the answer from here, which is going to be I comma j, the pair of indices which gave a sum equal to the target. So this is the whole logic of this algorithm, and let's try to analyze the time complexity of this algorithm. So we know that I always move towards right and j always move towards left, and this loop runs till I is less than j. So the total distance traveled by I and j, the sum of the distance traveled by I and j, will be equal to the length of the array, because the last operation would occur when I and j are just adjacent to each other. After that, our loop will break and our program will end. So the total distance traveled by both I and j will be equal to the size of the array. So the total time complexity of our problem is big O of n, where n is the size of the array. And we have not used any extra helper space. We have just used constant space to store the pointers and stuff. So again, the space complexity is big O of 1. So now we can see that we are maintaining our time complexity. We have done this question in a very optimized manner, and our time complexity was big O of n, and we have not used any extra space. So our space complexity is big O of 1. So now this two-pointer approach comes in really handy in a lot of questions, and you'll see this by yourself when you're practicing questions on online sites. You'll see that this two-pointer approach is going to be used in a lot of problems, and you'll be able to solve those problems with this approach in a very optimized manner. So now that we have understood all the four approaches, let's try to write the code and submit the code on Leetcode. Just one thing, so I'm going to only write the code for the second approach, that is the binary search approach, and the last approach. So the first and third approach are quite trivial, and I thought that writing code might not be really productive. For the second approach also, the second approach is also quite trivial, but since we are in binary search series, so it makes sense to do as much practice as possible for writing the binary search code. So let's first discuss the binary search approach. So for the binary search approach, this was our main method, which is going to be called, and we are passed an array of numbers, and we have been passed a target. So the input is an array and a target, and we need to return a pair of indices which are pointing to two elements whose sum is equal to the target. So as we discussed, we traverse through the whole array and we pick numbers one by one. So we are traversing through the array and picking numbers one by one, and we are trying to binary search the complementary of this number in the remaining array. So we are only going till the second last element, because for the last element the remaining array would be of size 0, and it would make no sense to do a binary search in a size 0 array. So we are going from the first element to the second last element. Then we are calculating the complementary of this number, which is nothing but target minus current number, and then we are calling our helper method to do a binary search. So this is the helper method call. Now we'll see this helper method in detail. So the helper method basically returns the index of the complementary number if it is present in the remaining array. If it is not present, it returns -1. So if it returns an index which is not -1, then definitely I found the complementary in the remaining array. So I have added the indices in my answer and I have returned the answer. So why I have added one in the indices while returning? Because in the question it was given that it is a one indexed array. So just a weird twist or a gimmick. So it's not a zero indexed array, and we are assuming everything is zero indexed in our logic. So in the end, I've just added 1 and returned the answer. Now let's try to understand the helper method. So for the helper method binary search, we actually take the input, which is the array, and we take two bounds int I and int j, which basically represent that what is the part, in which part of this array we are trying to do the binary search. So these are like the lower and the upper bounds of the array, and then the target, which is the complementary number we are trying to find out. So every time in the loop when we are calling the helper method, our remaining array is basically the numbers ahead of this number. So if I is the current index, my remaining array is from I plus 1 till the last index. So these I and j are representing those bounds, and this logic is nothing but a very simple binary search. So I have done a binary search taking I as the low and j is the high, finding a mid. If the mid is equal to target, return mid. Otherwise, if the element at mid is smaller than the target, then obviously I discard the left half. And if my element at mid is greater than the target, I discard the right half, and I do this binary search. If I'm not able to find this number, this loop will end, and outside this loop I've returned -1 as a indicator that I was not able to find the number. Now I wrote this solution on Leetcode and I submitted, and these are some of the stats when I submitted this question. So obviously it was accepted, and this was the runtime, and this was the memory usage. So now let's try to understand the second approach, or the main approach, the two pointer approach. So as we discussed, in this approach we will first initialize two pointers. So first pointer is initialized at index 0, and the next pointer and the j pointer is initialized towards the right extreme, which is the last index. Now I have made a loop, and in this loop I find the sum of the elements at these pointed by these two pointers. If my sum is greater than target, so we have already discussed, in that case j will move towards left. And if my sum is less than the target, we have already discussed that I will move towards right. So j moves in only one direction towards left when sum is greater, and I moves only in one direction towards left. The third case was when the sum of these two elements is equal to the target. So obviously if that is the case, we have found our answer, and I have returned the answer I comma j. And again this complete loop runs till I is less than j, because if I is equal to j, or I has crossed j, then my valid array, in first case my valid array is of size 1, so I cannot find a pair of size 2, and when they have crossed each other, my valid array is of size 0, so obviously I would not get an answer there. So definitely I will break my loop if I is greater than or equal to j. And in that case, obviously if that case arises, definitely we were not able to find an answer, because we never hit this condition and we never returned an answer. So I will just return an empty vector. Now I also submitted this solution on Leetcode and it was accepted, and these are some of the stats. Now you might see that the runtime for the previous approach is 24 millisecond, and the runtime for this approach is 23 millisecond. So you might feel that okay, we discussed that the time complexity for this approach is less, so it should have run in less time. So that is not the case. Don't take these 23 millisecond, the runtime stats, as the actual indicator of the fact that this approach is more efficient. According to me, when you do not have the premium subscription of Leetcode, you are not always given enough resources. So if the CPU time given to my code is less, or the resources given to my code is less, even if it might be efficient, it might run in more time. So these stats are not actually indicator of how efficient your solution is, because if I submit this solution 4-5 times, there is a chance that this runtime might increase. It might increase to 25-26. So don't take this as the indicator. But yeah, obviously when we were discussing the logic, we discussed that this is actually an efficient approach. The time complexity is much less for this approach, so this is efficient. But yeah, this 23 millisecond does not indicate that fact. So I guess we have covered all the four approaches, the code and everything. So with that, I think we can end this video here. If you still have any query, do mention in the comment section, and if not, see you in the next video. Till then, take care and keep learning.